So this is Math 317, what is this, lecture 4? So today's theme, not surprisingly, is on optimization. Given that my son was sick, we actually got to the doctor's office before they opened. If my wife had been able to stay around longer to take my daughter to school, we would have been the first person. One other group beat us there. Still was able to get here by 10 o'clock. I emailed that today would not be a general theory lecture, so I wanted to use today to just discuss problems. If there's some problems in the book or some problems with the material, I'm happy to do those. If not, I will start talking about the material that's in the video, the Euclidean algorithm, and how to analyze that. The cell phone policy is on hold for today, just in case Cam calls from his sickbed at our house. All right, so there will be no munchkins or anything like that. My son might be kind enough to try to call for you guys. All right, are there any problems from the book? I know some people have been asking me about problem number 4, which talks about trig tables, and you don't really need to use trig tables to multiply two numbers. The reason I mention trig tables is that there is a later problem that uses trigonometry. I did not assign that problem this year. And I just want you to be aware of where lookup tables are useful. So the Babylonians had lookup tables for multiplying numbers. You're like, we don't need lookup tables for multiplying, but we need lookup tables for other things. You know, trig values. Now, you guys are lucky. When I was in school, we had to learn how to use trig tables. We had to use log tables and all that stuff. If you go back another generation, they'll say, oh, I had it so lucky when they were in school. You know, it was uphill both directions from their house in the snow. You know, everybody always talks about the stuff they had to do. But it's amazing which stuff now you can just completely ignore because of the powerful computers you have. And you no longer have to have all of this information printed and accessible. I'll just mention one of my favorite things. How many of you have reference books for software? You know, for programs that you use? You know, when I was young, you had a reference book for Mathematica. Why don't you have reference books anymore? It's all online. Or the program can actually store it inside. You have so much space now that you don't have to worry about, well, we don't have enough room in the program for this. Right. Any questions from either the material or homework problems that haven't been assigned that people would like to see?
Sorry, homework problems that haven't been assigned?
Right. If you want to ask homework problems that have been assigned, we can see what happens. You know, if you want, I'll do the trig problem, which would be very similar to the Gaussian problem. All right, so trig. So I don't remember exactly how it's phrased in the book, so I'll just do something similar. So imagine you know sine of theta. Theta is in 0, 1, 2, 3, let's say 90 degrees. Should we ever do trigonometry in degrees? There's no reason ever to do trigonometry in degrees.
Do you work with engineers?
So if you work with engineers, how would you write the square root of -1 if you work with engineers? What?
You would.
It's J. For engineers, the square root of -1 is J. The reason is they use I for current. And so they protect the symbol I. It's just good to know the notations people use. There are times when you want to use degrees. If you are just caring about sines and cosines of angles, it's often much easier to just think in terms of degrees than radians. That's fine. Since we have a little bit of time today, I will teach you all trigonometry at one point in 5 minutes. There is, however, a key reason why we like to use radians. And the reason is for differentiation in calculus. What's the derivative of sine? What's the derivative of cosine? Right, and the mnemonic I like to use is one of these derivatives has to have a minus sign. Where does the minus sign go? Minus sign. Ah, yeah. Ah, ooh. Okay. If you do trigonometry in degrees, then the derivative of sine is no longer cosine, and the derivative of cosine is no longer minus sine. there's a conversion factor. And by using radians, everything is nice. That's the whole point, is you want to look at the limit as h goes to 0 of sine of x plus h minus sine of x over h. And that will be the derivative of sine. Similarly, you look for the derivative of cosine. Out of curiosity, and if you've seen me do this before, please don't answer. What's the limit as h goes to 0 of sine of h over h? What would that limit be? So what is this limit? Yes?
Isn't it 1?
It's 1. Good. How would you get that? Because we've got 0 over 0. How would you handle that? You could L'Hopital it. You know you've made it when your name is a verb. Okay? That's the pinnacle of success in science. You L'Hopital it. And the only thing better than L'Hopitaling something once is L'Hopitaling it multiple times. But one L'Hopital is enough. You'll get the limit as h goes to 0. What's the derivative of sine? Cosine. Derivative of h is just 1. Well, what's cosine of 0? 1. So you get 1. Unfortunately, this argument is somewhat flawed. It's very subtle. What's the mistake with this argument? How did you know the derivative of sine was cosine? You need to know this limit when x equals 0, right? What's the sine of 0? So to know that the derivative of sine is cosine, you have to compute this limit. So to compute this limit, you're saying, well, the sine, its derivative is cosine. We don't know that yet. You can't use L'Hopital here. You have to go through the long way. Now what's nice is if you want to calculate, say, the derivative of sine x, this is the limit as h goes to 0 of sine of x plus h minus sine of x over h. This is the limit as h goes to 0, sine x cosine h, right? Plus cosine x sine h minus sine of x over h. Now when you look at this, we have 3 terms in the numerator. Which term should be the odd term out? I'm sorry? So one thing is sine of x, it's all by its lonesome. Everything else has 2 factors. Also, sine of x has no h in it at all. But I think 2 of these 3 terms really want to be together. Yeah?
Sine x cosine h and minus sine of x.
Yeah, they both have a sine of x. I can split this as I can pass it out the limit. Sine of x, the limit as h goes to 0 of cosine of h minus 1 over h plus cosine x, limit as h goes to 0 of sine of h. Over h. What's another way to write 1? How else can you write 1? Yes? We can write it as cosine of 0. So we can really view this as cosine of 0 plus h minus the cosine of 0. And similarly, I can write sine of h as sine of 0 plus h minus the sine of 0. And what this tells us is if we want to take the derivative of sine at any point, it's going to be sine of x times this limit plus cosine of x times that limit. And we only have to evaluate 2 limits now. All trigonometry reduces to finding these 2 limits. I'm assuming at this point that we know the angle addition formula for sine. Okay. I like this argument because it really highlights how to look at algebra, how to view things. So I will say just a little bit more on where things come from, and then we'll do how to actually get the sine table. So Has everyone seen e to the ix is cosine x plus I sine x? Sometimes called Euler's formula. Is anybody who has not seen this? Okay, this is in competition for one of the most beautiful formulas in all of mathematics. So if I give you some point in the complex plane, say on a unit circle, here's theta. This is going to be cosine x here, and then this height here will be sine of x. And this point is going to be cosine x plus I sine of x. Now when you think about how the function is defined, we define e to the x as the sum, n goes from 0 to infinity, of x to the n over n factorial. What is e to the x times e to the y? E to the x plus y. That's a theorem. It is technically the sum, n goes from 0 to infinity, x to the n over n factorial, times the sum, m goes from 0 to infinity, y to the m over m factorial. And then you have to do some algebra and use the binomial theorem to show that this is the same as the sum k goes from 0 to infinity of x plus y to the k over k factorial. If this were not true, and this is just e to the x plus y, then this would be horrible notation. What's 1 over cosine? Secant. What's 1 over sine? If you could choose, would you have cosine associated with cosecant and sine associated with secant? I would. Mathematics has bad notation. I blame physicists. But you want notation that is useful. If this were not true, if e to the x, e to the y was not e to the x plus y, then this would be terrible notation for the exponential function. You are thinking about taking a number and raising it to a power. This has to be proved. So as a nice exercise, try to prove this. The hint is the binomial theorem. Okay? So we can prove all of trigonometry from this formula. And this will give you another sense of where these trig identities come from. And this is all going to be extremely useful for doing the original problem of finding a table to interpolate sines. So e to the ix times e to the minus ix is what? 1. Because it's just everybody agrees, there's e to the 0. This is also cosine x plus I sine x times cosine x minus I sine x. And what I'm using here is e to the ix is cosine x plus I sine x. If x is negative, then I have the sine of negative x. The sine of negative x is negative sine x. So using sine of negative x is negative sine of x. When you expand this out, the real part is cosine times cosine, and then I sine times minus I sine. So you're going to get that this is cosine squared x. What's I times minus I? 1. So you have negative I squared is negative 1, so you get just plus sine squared x. Sine x cosine x times I minus sine x cosine x. So we get cosine squared plus sine squared is 1. There's Pythagoras. E to the ix, e to the iy is e to the I x plus y. This is going to be cosine x plus y plus I sine x plus y. If I expand this out, cosine x plus I sine x, cosine y plus I sine y. If I expand this out, the real part here has to be the real part here. The imaginary part here has to be the imaginary part there. If two complex numbers are equal, it's like vectors. The only way two vectors can be equal is if each component is equal. For complex numbers, the only way two complex numbers can be equal is if the real parts are the same, the imaginary parts are the same. This is where the identities for sines and cosines come from. It all comes from the exponential function. The angle addition formulas, the half angle formulas, you can get all of these by playing games here. So if you ever forget trigonometry, you can now rederive it just from this. What this tells us is there's tremendous connections between these functions. So if I can understand the sine of x, I can understand the sine of twice x. I could also get the sine of x over 2. So a lot of these problems ask you to find ways to interpolate values. So I want a formula for the sine of x halves. And let's assume we know the sine of x. And if we know the sine of x, what else do we know? Oh, we would know. We would know sine 2x. We would know that, but we also know something else. We know sine. You know the cosine. You could get cosine by Pythagoras and then just figuring out is it positive or negative. Also, there's a relationship between sines and cosines. You know, one is like pi halves minus the other. So if I know sine of x, I know cosine of x. How can I get sine of x halves in terms of these? Well, if I look at the sine of x halves plus x halves, if I use my formula, this is going to be the sine of x halves cosine x halves plus cosine x halves sine of x halves. I'm hoping I'm doing this the right way. So we get the sine of x is going to be 2 sine x halves cosine x halves. Can we use this to solve for the sine of x halves? Yes.
Yeah, if you substitute, oh wait, no, never mind, that gives you 2, that gives you the sine 2.
So again, we now consider this as being known.
What if I try Pythagoras on cosine?
Yes. It's going to be pain. The sine of x is 2 sine of x halves, and then cosine would be the square root of 1 minus sine squared x halves. Then I could square both sides, and I would get sine squared x is 4 sine squared x halves, 1 minus sine squared x halves. I see at least one smile. I can't quite see my smile. Oh wait, no, I can. I can look. Yes, I can see my smile. Good, I see 2 smiles. So this looks like a quartic equation. Is it really a quartic equation? No, it's a quadratic equation with pretense. Because notice that it's only the sine squared of x halves that comes into play. So this is really a quadratic equation in sine squared. I can use the quadratic formula and solve for sine squared. And then I can take the square root of that and get the sine of x halves. That's one way to do this problem. The other way to do the problem is instead of trying to use a formula for the sine of x halves plus x halves, what else could we use? What other formula could we try? So if I want to calculate sine of x halves, instead of calculating sine of x halves, what else could I calculate? And if I know that, I can get sine of x halves immediately. And it's similar to something we did in here. So if you know the sine of x halves, let's look at this over here. Instead of calculating the sine of x halves, that's going to be, so I want this to be now maybe the angle x halves. So this would be sine of x halves. This would be cosine of x halves. If I can calculate the cosine of x halves, then I can immediately get the sine by just doing the square root of 1 minus that squared. So the question is always, which is the best thing to look at? Sometimes it's easier to calculate something else first. And so now, what I could do is I could do the cosine of x halves plus x halves, that's going to be cosine x halves squared minus sine squared x halves, right? So you get cosine of x is cosine squared of x halves minus 1 minus cosine squared of x halves. So we are doing something very similar as before. We are still using Pythagoras. It's good to see what tools you use. And now we get cosine of x is twice cosine squared x halves minus 1. So cosine of x halves is the square root of cosine x plus 1 over 2 if I haven't made any algebra mistakes. And now that we know cosine of x halves, now we can get sine of x halves easily. So it's worth just getting a sense of what can you compute from something. So if we know the angles from 0 to 90, what else do we immediately get?
The half.
Yeah, we immediately get the halves. So if the problem is, can you find a way to interpolate? Well, we don't even need to interpolate. We could actually get the values exactly for something like 22.5 degrees. We know what the sine of 45 is. We can take half of that. So we can actually get a huge number of things. And then the question is, which numbers will be obtainable for us? It should be anything, any rational whose denominator is a power of 2. Because if I do it once, I get everything that's either an integer or a half integer. I do it again, I get anything that's an integer, a half integer, or a quarter integer. If you wanted, you could also get maybe something by looking at maybe the three-angle identity. And maybe you could get something like that. Or maybe you just find a rational with a really close, for any rational number, where the denominator is a power of 2, you can always find a number like that that's pretty close to whatever real number I give you. And that could be one way to interpolate. So this is using really detailed properties of sines and cosines. And so what we're doing is, by having a couple of values stored, we can then use these formulas to get a tremendous number of other values exactly. The question becomes, of course, can you work with these? We're now starting to take square roots and then square roots of square roots. You can keep the formulas exact. That's one of the advantages of using a system like Mathematica. It will keep the formulas exact. And it will only approximate them when you finally tell it to. All right. So that's one way to interpolate. Let's talk about another. So let's say here is 5, here is 6. We know the sine of 5. We know the sine of 6. I'm sorry, the cosine of 5. And over here we know the sine of 6 and the cosine of 6. And I want to calculate what's going on at 5.2. So I want to interpolate between these two known values. It doesn't have to be perfect. What we were doing before was going to be perfect. But sometimes you spend too much time trying to make something so perfect and so exact when those extra degrees of precision are useless to you. Okay. Quantum mechanics can measure things to, the best phrasing I've heard is, imagine you want to know the distance between Los Angeles and Boston. We can measure that to within the thickness of a human hair in terms of some of the calculations we do in quantum mechanics. All right. If I'm American Airlines and I'm flying a route and I need to know how much fuel I'm going to need, I really don't need to know the distance between Boston and Los Angeles to within the thickness of a human hair. And I don't care if it's the long way or the short way. Either one is fine. You don't need that much precision. You don't want to spend that much time gathering that much data. You just want a pretty good answer that's fast. Can anybody give me a way that I could try to figure out what the answer should be at 5.2? So to some extent, I want a formula that uses these as inputs And if I have the value 5, it's got to reduce to sine of 5. If I have the value of 6, it's got to reduce to the sine of 6.
So this would be using the half. I mean, basically you could use half of each to get 5 and a half.
Right.
And then use half of 5 and a half and half of 5 to get 5.25, which is probably close enough. But that would require 2 calculations.
So good. But I mean, again, right now, but the fast calculations. And what you're really doing is, let's look at this. So you first have half of sine of 5 plus half of sine of 6. Right?
Sorry, I meant sine, or yeah, sorry.
Right, this is what you meant, is to say, and that will be my approximation. Oh, you actually saying compute it exactly?
Yeah, which was why I was
Okay.
taking too long. But,
Right.
Yeah.
Well, I mean, it's not going to be too bad to do that exactly. I want to try to use just these values now. So let's assume we only have these values. We could use those formulas from before, but I want to try to use those values. I thought you were basically saying, let's average those values. And then that will give me the sine of 5.5. And then maybe I average the sine of 5 in that. And so maybe I would take that over 2 and take 1/2 the sine of 5. And use that as my approximation. Now, if I look at this, I'm going to get 3/4 the sine of 5 plus 1/4 the sine of 6. These two numbers, what do they add up to? They add up to 1. So basically what I'm saying is I'm assigning weights to the value of sine of 5 and sine of 6. And I'm going to have sine of 5 weighted more heavily because I'm closer to 5 than I am to 6.
Why for the weights wouldn't you just choose the distance? Like, so instead of 3/4, choose 0.8 and 1/4 choose 0.2?
Yes. So that would be a better way to do that. So the idea that was coming from over here was, let me take the halfway point, and then let me take halfway between that, and that should be a good approximation. This is essentially doing the powers of 2 that we were talking about before. And we could actually calculate these numbers exactly if we wanted to have this as a precise measurement. But what you're saying is, well, why not just do, it should be 0.8 sine of 5 plus 0.2 sine of 6. And if we do that, we're going to weight this one more heavily. So in general, if we go to some distance t, we would want to have 1 minus t sine of 5 plus t sine of 6. And what's nice about that is when t is 0, all of the mass is at sine of 5, and you don't see sine of 6 at all. When t is 1, all of the mass is at 6. Is there any other value of t that has nice intuition? So we had t equals 0, t equals 1. Any other good values of t to look at? Yeah, 1/2. So if we take t equals 1/2, that's the middle point, and it would be half of each. So whenever you have a formula, you always want to test as many cases as you can to see, is this reasonable? So this is a really good way to interpolate sine. Yes?
What about, I think what I would want to do here is use Euler's method to do like sine 5 plus 0.2 cosine 5. Well, you need to convert.
Okay, so why are you doing 0.2 cosine? I'm not saying you're wrong. And I don't think I would say Euler. I would say somebody else's name.
Well, it's not exactly 0.2. You need to add a 180 over 5 multiplier. This is degrees, I'm assuming.
Right. But it's not Euler's method. You're close, though.
Is it Newton method?
Not Newton.
Close. Another time.
So why were you adding cosine? Where did the cosine of 5 come in?
It's the derivative.
It's the derivative. So you're using the value of the function and the value of the derivative. Whose method is this? It's the difference between 150 and 151. If you take one, how many of you took 151? If you did 151 here at Williams, they assume you know a certain material. Taylor series. right? So you might remember the mean value theorem. At some point in time, you are traveling at the average speed. So at some point in time, your instantaneous speed is your average speed. The whole idea of Taylor series is the more information you have at a point, the more you should know about what's going on for some distance afterwards. If you're driving from Boston to, let's say, Philadelphia on 95, it's very hard to choose a starting time where the entire trip will be pleasant. There are just too many damn cities on the East Coast. You will hit one of them at a bad time. Your instantaneous speed could change wildly during the trip. If I wanted to estimate my speed at any moment in time, the more information I have, the better. Imagine the only thing I know is where am I? What would you estimate your speed as?
The time it took to do the trip divided by distance.
Yeah, so one thing I could do is just like, if I know the total time of the trip, I'll just say my instantaneous speed at that, my best guess is going to be my average speed. What if I don't tell you the time of the trip? And I don't even tell you which direction you're driving. What's your best guess for the speed? Yes?
Speed limit.
I'm sorry?
Speed limit.
It's actually pronounced recommendations. But if you don't know which direction you're going, am I going from Boston to Philly or Philly to Boston? What's your best guess for your instantaneous speed if all I tell you is a location? 0. Right? We don't know which way we're going. So the way Taylor series work, out of curiosity, how many people have not seen Taylor series or are not comfortable with like a review of Taylor series? Okay, so this is good. This is one of the things that sometimes falls through the cracks, and it's hard to fill in things like this. It's nice when we actually have a day like this and we could actually stop and talk about something like Taylor series. So F is my distance, and I'll do T as my time. And so I want to figure out where am I at some time X. And I know where I am at the start. So my first best guess is just my distance never changes. I always stay at the origin. This would lead to the theory of thermostatics, where nothing ever changes. It would be extremely boring. If you could get one extra piece of information, what would you ask for on your wish list?
FFT.
I'm sorry?
FFT.
Well, that's an infinite number of pieces of information. You know, I'm giving you f of 0. I'm giving you your location at time 0. You can ask me for one more number. F prime of 0. And then what I would say is, well, my next best guess is it's f prime of 0 times t. Oh, sorry, I guess I'm using x now. And I'll do x minus 0. So this is elapsed time. Speed times elapsed time would be distance traveled. So this would be a first order Taylor series expansion. And then if you could have another piece of information, what would you ask for? The second derivative. What is your acceleration? Plus f double prime of 0 over 2 factorial x minus 0 squared. And the reason you have 2 factorial is you want, instead of f, I'm going to write this as t sub 2 of f, the second order Taylor series of f. And I want this to match my function as much as possible. So when I do it like this, I'll get t2f of 0 is f of 0, t2f prime of 0 is f prime of 0, and t2f double prime of 0 is f double prime of 0. Is the first 3 derivatives match. And when I take 2 derivatives, well, since I have an x minus 0 squared, I'm going to get a 2 factorial coming down that cancels with the 2 factorial here. 2 derivatives kills these 2 terms. The x minus 0 cubed term, when I take 2 derivatives, it's still going to have an x minus 0. It will still vanish when I put in x equals 0. So by doing a series like this, it's going to ensure that they match at the origin up to order 2 for the derivatives. If I wanted to do the third order Taylor series, I would just have an f triple prime of 0 over 3 factorial times x minus 0 cubed. All right. Because of the beauty of sines and cosines, What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. So if I want to do a Taylor series expansion, normally, this is an oh shit moment, I would have to calculate the derivative of my function at this point. And I would need a new lookup table because I have a new function. But if you're doing the lookup table for trig, if you're doing the lookup table for sines and cosines, what's the derivative of sine? It's cosine. We already know those values. And then the second derivative would be negative sine. So we could actually calculate a Taylor series very easily from a lookup table. And we can interpolate with incredible accuracy. Just take a couple of terms. We can even have bounds as to how much our error will be. If you want to be within a certain threshold, well, what's the largest any of our derivatives are going to be in absolute value? 1. And so and what's the largest x could be in absolute value? 1. We're always going to be between, and we have a factorial that's increasing very rapidly. So if you want to have a lot of accuracy, it's very easy to do that here. So this is a tremendous amount of discussion for a lookup table for sine. But there's a lot of really good ideas here. It allows us to review Taylor series. It allows us to say, if there's certain information that you know, try to find a way to exploit that. There's many different ways you could interpolate. We can calculate the derivatives easily. Let's try to bring them into play. Out of curiosity, how many of you remember multivariable Taylor series? And calculating the partial derivatives? Okay. The camera can't show that everybody was enthusiastically and vigorously shaking their hands and praising the multivariable calculus teachers that they have had over the years. So as long as we're here, let's quickly do multivariable Taylor series. It's like Taylor series, but in simple dimensions. So you just have to start taking more and more derivatives. So you would have f of 0, 0. And then you would have df dx at 0, 0 times x, plus df dy at 0, 0 times y. And then you start having the joy of you'll have d squared f dx squared at 0, 0 x squared. And then, oh crap, what factor goes here? Is it a 2? Is it a half? D squared f dx dy at 0, 0 xy plus d squared f dy squared y squared, and so on and so on and so on. Well, maybe there's a factor. Well, actually, we know we have to have a half here, and we know we have to have a half here. Because if there's no y dependence, it has to reduce to a one-variable Taylor series. So I know I have to have a 1/2 here. If I take 2 derivatives with respect to x, the x squared is going to have to cancel the 2 factorials. When I take a derivative with respect to x and a derivative with respect to y, I just get 1. So in fact, this factor here should just be a 1. And you can then continue, and you can go on to 3 derivatives, and 4 derivatives, and 5 derivatives. Okay? Given that this is a class on efficiency and optimization, oh yes. So I need things to match up. And so when I take the derivative with respect to x and the derivative with respect to y, I'm going to just get 1 from that and 1 from that. So if I had any fraction here, it would not equal d squared f dx dy. All right. So does this seem vaguely familiar to anybody? Vaguely, at least. I mean, come on. I mean, with the word vaguely, I'm not asking for much, guys. I'm going to show you a trick that will allow you to do almost any multivariable Taylor series trivially. So let's say I give you the sine of x squared y plus x minus y. So we just take the partials with respect to x, with respect to y, then twice with respect to x, twice with respect to y, and once with respect to x, and once with respect to y. Okay? Does anybody want to do that? Right, here's the trick. What's the Taylor series of the sine of u? These are approximations you should know. Well, it's not, I'm using u as the variable, so yes.
U minus u cubed over factorial plus u because over factorial.
Great. Right? That's the expansion of sine of u. Let u equal x squared y plus x minus y. How many people have seen this? Okay. This is a wonderful, wonderful trick to make multivariable Taylor series much nicer. If you have a function you understand, just plug in the new input. So now I would have x squared y plus x minus y minus x squared y plus x minus y cubed over 3 factorial. Now, this function is a little bit annoying, deliberately so, because the terms don't have the same degree. This term is degree 4, degree 1, degree 1. When I look at this term here, cubed, what's the smallest degree we're going to have when we expand this? Yes?
Sorry, isn't the first term degree 3?
I'm sorry, the first term is degree 3, yes.
Okay, so the biggest for that one would be degree 9.
The biggest would be degree 9, and the smallest would be
3.
3, because we have an x and a y, so we cube it. For the next one, with the u to the 5th, the smallest would be degree 5, the largest would be degree 15. So if I wanted to find all terms, if I want to find the third order Taylor series expansion, I don't have to worry about the u to the 5th terms. That's already going to be of degree at least 5. If I want just the third order Taylor series, all I have to do is take this and take only the terms of degree up to 3 here. If I want the second order Taylor series expansion, do I even need to use any of these terms? No. Second order Taylor is just going to be x minus y. Actually, that's it. That would be the second order Taylor series expansion. Much faster than using the partial derivatives and the expansions. So there are many sayings about mathematicians. We like to reduce things to a previously solved problem. One of my favorite jokes is a mathematician and an engineer, could actually be myself and my brother, are walking down the street and they see a house and the house is on fire. Fortunately, there's a fire hydrant outside the house with a hose next to it but not connected. The mathematician connects the hose, turns it on, puts out the fire. They keep walking, and a little bit later they come to another house that's fine, and there's a fire hydrant with a hose that's connected. The mathematician carefully disconnects the hose and sets the house on fire, thereby reducing it to a previously solved problem, and continues walking, as the engineer just looks on in disgust. We like to reduce things to things we already know. This is one of the themes that you should be getting out of your classes. What do you know? How can you take whatever you are given and convert it to something that you know? Right. We don't have many times in our college careers where we could actually just sit and wax philosophical, look at what have we maybe missed in our previous classes, or now that we've gone a little bit further, how can we put the pieces together and see how they fit in? But I don't know why the camera is moving. So when you're looking at things like this, always ask, what do you know how to do well? So I often talk about the principle of the hammer. If you have a hammer, pretty soon every problem looks like a nail. You'll find a way to make it look like a nail because you're a master at the hammer and you can just smash it. There's another corollary to this. If you are really good at the hammer, go to the land of the screwdriver. Because if they could have solved their problems using a screwdriver, they would have solved it by now. They're smart people, at least some of them. If you have a different tool set, if you have a different set of skills, well, they've already tried the things they can do. Now you try the things that you know how. I've written a lot of papers outside of pure mathematics where I've used number theory. Well, most marketing professors haven't been trained in number theory. If they could have done it using their standard techniques, they would have done so. If you have diverse perspectives, it is tremendously valuable. You don't want everybody to have the same skill sets. You want to be able to look at things, well, how could you attack this? Anybody ever read Richard Feynman's works? There's a lot of very funny stories. So he talks about how he got this reputation for being a phenomenal integrator. Is people would come to him and they'd be stuck on an integral, and he would solve it almost immediately. And he writes, well, this is Princeton, this is MIT. These are not idiots who are coming to me. These are top graduate students and whatnot. They've tried almost surely every standard technique, And if it could have been done with the standard techniques, they would have done so. I'm not going to waste my time on that. I'm going to assume they've done their job right. Most people don't know the technique differentiating under the integral sign. Let me see if that works. And it will almost always work. You know, because it's one of those problems that it is fortunately a nice answer, and this is just a technique people don't know. If you remember your calculus, maybe partial fractions would be the equivalent where I think that's the least favorite of all the integration techniques, but it's very powerful for solving a lot of problems. All right, so for the rest of the homework, there is a problem on finding a lookup table for a Gaussian, where a lot of these ideas will be useful for something like that. But it's, again, always think back to what do you know and how can you put it in context. So I will end with, has anybody ever watched a presidential debate? Okay. It does not matter who the candidate is. Whatever question they ask, it's probably not bad that's not looking at me as I'm saying this, but it doesn't really matter who the candidate is. They have something that they want to say. They've got their story, their point, their soundbite that they want to make. So whatever question they ask, oh, that's a great question, and they meander for a little bit, and then eventually you can tell when they hit the part where they've memorized, and here's the story that they want to say, and they're just working to get that answer in from whatever question was asked. You want to be able to do that mathematically. When you are doing a problem, what do you know? What are your skills? What are your assets? How can you work that in? So for the sines and cosines, Taylor series is a great way to interpolate because we know the derivatives without any trouble. All right, have a great weekend.